Hello. Hello. My name is Seok-jin Shin. I am currently attending Chungbuk National University Department of Information and Communication Engineering. The presentation topic is implementation of Edge platform for smart farm using MQTT and Kafka. This is index of the presentation. This presentation goes from the introduction to the conclusion sequentially. Introduction. The agriculture sector will face tremendous challenges to feed the 9.6 billion people projected to live on the planet by 2050. The FAO estimates that food production must increase by at least 70% by 2050. To solve those challenges, the agriculture sector must adopt smart farms. AIoTI defines smart farms as applications of data collection, processing, analysis, and automation technologies across the entire value chain. So, most smart farms incorporate IoT technology to transmit and receive real-time data from sensors and manage them. It can help evaluate field variables such as soil state, atmospheric conditions, and biomass of plants or animals. It can also be used to assess and control variables such as temperature, humidity, vibrations, or shocks during product transport. Therefore, the application of IoT technology in the agriculture sector can control the efficiency of resource use and significantly improve production capacity. However, there are several challenges that need to be addressed in order to adopt IoT technology. One of them is processing and analyzing vast amounts of data coming from heterogeneous devices. Furthermore, processing all these collected data directly to a central server is inefficient and sometimes, in particular, due to limited communication and storage resources, overall energy and cost, and unreliable latency. To address these challenges, we introduced the concept of edge platform, where data processing tasks are pushed to the edge of the network. There are two major elements of the edge platform implemented in this study: MQTT broker and Kafka server. The MQTT broker is responsible for exchanging messages between various sensors and actuators in the smartphone, and Kafka reliably sends large amounts of data generated in the smartphone to consumers. Background: MQTT is a server publish subscribe messaging transport protocol designed to be open, simple, and easy for clients to implement. Because of these characteristics, they are used in many contexts, including limited environments such as machine-to-machine communications and Internet of Things. MQTT today is used in a wide variety of industries such as automotive, manufacturing, telecommunications, oil and gas, etc. Reliability of message delivery is important for many IoT use cases. This is why MQTT has three defined quality of service levels: QoS, 0 at most once, 1 at least once, 2 exactly once. QoS refers to a level that guarantees the quality of service. An appropriate QoS level should be selected according to the type of service. In this study, the QoS level was set to 0 because speed is prioritized over reliability of data generated by sensors. This is the figure for describing MQTT broker pattern. Client B and client C subscribe topic temperature, and then client A publishes same topic to MQTT broker with value 24 degrees Celsius. After broker receives topic value pair, broker forward it to all subscribers. After collecting the sensor data generated from the sensor module located in the smartphone through the edge platform, it is processed to be classified as an MQTT component by topic. Apache Kafka is an open-source distributed event streaming platform for high-performance data pipelines, streaming analytics, data integration, and mission-critical applications. It provides a publish-subscribe messaging model for data production and consumption, and supports the ability to access data in real time for real-time stream processing by allowing long-term storage of data. Kafka was designed from the ground up to provide long-term data storage and data reply. Apache Kafka has a unique approach to data persistence, fault tolerance, and reply. Therefore, this can be seen in how it handles scalability by allowing data access using cross-partition data sharing, topic partitions, data offsets, and consumer group names for data replication processes in clusters, increased data volume and load. Apache Kafka is also well suited for real-time stream processing applications because it is designed to act as a communication layer for real-time log processing. This makes Apache Kafka suitable for applications running on communications infrastructure that process large amounts of data in real time. Every partition has one server that acts as the reader for all read-write operations within the server, and the other server acts as a follower of this reader. If a reader goes down or fails, by default one of the followers on the other server is chosen as the new reader. Producer can generate specific messages coming to selected partitions with a topic. Consumers can consume publish messages based on topic. Messages are delivered to consumer instance within the subscribing consumer group. The topic partition data is transmitted to the server Kafka cluster and replicated to each broker in the cluster, each partition of the server. Afterwards, at the request of the consumer group, each broker in the Kafka cluster designs a system capable of distributing data and transmitting large amounts of data. Edge platform. Data is increasingly produced at the edge of the network. Therefore, it would be more efficient to also process the data at the edge of the network. Edge computing refers to the enabling technologies allowing computation to be performed at the edge of the network on downstream data on behalf of cloud services and upstream data on behalf of IoT services. Edge computing represents a paradigm shift from centralized to decentralized. Improve QoE by using compute resources closer to the client. The environment built for this is called the Edge platform. Edge platform eliminates bottlenecks and partial points of failure and enables rapid recovery from failures. For this reason, Edge platforms aim to reduce response time or latency by caching content. The Edge platform can be used wherever edge computing is used, such as location-based, Internet of Things, data caching, big data, and sensor monitoring activity spaces, mobile cloud, and others. Implementation. Hardware architecture. This study does not constitute all environments used for smartphones. It is designed for direct application to real agriculture using the Raspberry Pi Zero W with minimal resources. 1 GHz single core CPU, 512 MB RAM, and also very cheap. Therefore, it is very easy to use in agriculture. Each hardware operates on an independent IoT device and communicates with edge nodes using the MQTT protocol, which is relatively lightweight compared to HTTP. Each hardware interacts with the edge platform and exchanges large amounts of data. Each sensor is not interconnected and operates through an edge platform. This means that data can be processed efficiently without unnecessary communication. The following addresses in Table 1 are used to access RAM and read-only information. TA is the ambient temperature of the object, and T object 1 and T object 2 are temperature of the object. The result has a resolution of 0.02 degrees Celsius and is available in RAM. 2 is derived from RAM as target object Kelvin equal target object regular multiply 0.02 or 0.02 Kelvin per LSB. Table 2 shows the modules used in this study. The runtime in which the server runs is composed of Node.js based on the JavaScript language, and a package suited for Node.js is configured so that the server can work well. The whole system consists of an edge platform with multiple MQTT clients and multiple edge nodes. Each client connects to the edge platform to send and receive data. The edge node is mainly composed of two components, the MQTT component and the Kafka server. The MQTT component is a broker and subscriber to the MQTT protocol. This allows for immediate data transfer as well as other operations after receiving the data. In this study, specific data is sent to Kafka after receiving data from a component for reliable data storage and transmission. When a sensor publishes data on a specific topic, the MQTT component receives it and classifies it into direct processing data and data processing through Kafka. Software architecture. Many sensor data take constant values except under special circumstances. However, under special circumstances, it exhibits unusual values. In this case, it is important to reliably transfer the desired data between successive sets of data. Kafka within the edge platform does this, and in Kafka, the received data is shared on the edge platform, and data is shared with multiple consumers who consume the data, server processing data, and sent to different services. When data is sent through Kafka, consumers of such as database and web servers consume the data immediately and proceed as follows. The web dashboard utilizes the sensor data delivered to the DB through the edge platform to visualize it through a graph tool on the web. Communicates with the edge platform through a web socket and checks the status of the smartphone in real world. Conclusion. Smartphones can be built easily and quickly through the edge platform using MQTT and Kafka implemented in this study. In smartphones, efficiency can be increased based on massive sensor data, and sales can be expected to increase as production increases. In addition, as the time and technology required to build a smartphone decreases, the burden of continuous change and introduction of technology is expected to decrease. Through the smartphone edge platform, technology using MQTT and Kafka developed in this study, we can expect to increase the sales of the phone and contribute to the continuous development of big data-based services in the future. In addition, the edge platform is expected to reduce the cost of sensor replacement by contributing to compatibility in rare forms where sensors need to be constantly replaced. Thank you.